Kristen.
Yeah, ethanoic acid has the lowest vapor pressure. This bottom line here. Lowest vapor pressure at any temperature. It's the lowest vapor pressure. Good job. 5. Which one has the strongest forces of attraction? Explain why or how you know. Isla. Good. How do you know? Okay, it takes a higher temperature for it to evaporate. It also takes higher temperature to do what? To boil, right. So ethanoic acid has the highest boiling point. That's how we know it has the strongest forces. What else could we say? What else information on that chart tells us ethanoic acid has the strongest forces of attraction? Shelby, what do you think? Besides boiling point. So right here has the highest boiling point, so that means it has the strongest forces. But what else on this chart tells us it has the strongest forces? Takes longer to increase, yep. Okay, I'll leave you alone. Evan. Yeah, it has the lowest vapor pressure at any temperature. What does that mean, Blake? If something has a low vapor pressure, what does that mean? Don't say it has strong forces, because yes, it does. But... or not, did I say Blake or Jake?
Blake.
Blake, yeah.
You know.
What do you think? What does low vapor pressure mean?
I was going to say it has strong forces.
Good. Zach, help me out.
What?
What does low vapor pressure mean? Something has low vapor pressure, what does that mean?
It takes longer for stuff to break apart.
Good, it takes longer for the liquid to break apart, which means there's less collisions because there's less what? Yeah, less vapor. That's what that means. So if this liquid had really low vapor pressure, what would it never do? Evaporate. Like this table has really low vapor pressure. It doesn't evaporate. This table's never going to evaporate. Okay, and just be gone. So this liquid, if it had low vapor pressure, means above it, less collisions. So that's what that means. That means strong forces, like Blake said. Good. 6, which has the weakest forces? Edwin.
Propanol.
Propanol, right here. How do you know?
Because it takes the least amount of heat to boil.
Least amount of heat to boil, lowest boiling point, and it has the highest vapor pressure. Either answer would work. If you want to focus on boiling point, that's probably a safe bet. So it has the lowest boiling point, weakest forces. Good job. Pass those up. Make sure your name's on it.
Christian McQuay?
Yes, sir.
Yeah, I go to the bathroom.
You may.
Alright.
Okay, now we're going over the homework. Pass them up. Oh, pass them all over to Devin. Go collect them all. And you do not have homework. So that's good. Let's go. What's going on here? Pass them up.
It was taken care of.
I got another question for you though before we go. Take your homework out or get that out in front of you. Devin, after class, I want to read you those book answers. Sometimes I forget to do that. I wrote a note to myself here. Why does boiling point decrease when air pressure decreases? So why does water boil at 69 degrees on top of Mount Everest?
Oh, because
Go ahead, Ryan.
there's less air pressure pushing down, so it's like the water pushes out the area.
Good. So there's less. So if this water was on Mount Everest, right, it's got a certain amount of vapor pressure pushing up against the air. If the air pressure on top of the mountain is less, right, so less force, then it's going to need less energy to push back. So it boils much quicker at a lower temperature. Good. So the same explanation in reverse. Why, when you get closer to sea level, does the boiling point go up? Because there's more air pressure, right? So if there's more pressure pushing down on the liquid, you need more energy pushing up. So I didn't review that too much yesterday. I wanted to talk about that. The homework covers some of the concepts I want to review with you, so we'll just hit the homework here. And then...
so does that mean in Lake Death Valley it takes longer to boil water?
yeah, because isn't it like below sea level? Yeah. Yep. So the lower your elevation, the higher the boiling point. So yeah, it should be above 100, technically.
If it's below sea level, shouldn't there be water there?
Yeah, but it's land.
But if you like go below.
Right. I mean, but the concept there is, I think, I don't know. It's like the ocean. technically sea level, right? So you can go below that in other parts of the world. It's
Like
just,
a Rift Valley in Africa. Or
yeah, like a
something.
valley.
It's
Yeah.
ridiculous.
In other words, there isn't always water where there's depression in the ground, right? There should be.
Yeah.
Okay.
It's
It's not like there's just one layer of water. I mean, there's a water table, right, which is deep down, and that's where we drill for wells. But there isn't like one layer that covers everything, right? It's in different spots. It kind of accumulates in certain areas. Yeah, I mean it's a good concept though. I mean you would make sense if it's below sea level, it should be underwater. That makes sense.
Cool,
But
That's probably what happened to Atlantis, to be honest with you.
probably. All right, 20. So we're on this side. Okay, we're on this side. 20. I'm gonna go through a bunch of these myself here to speed it up. It's actually gonna take us a while. This was a lot of work. Okay, so I guess it's good you don't have homework tonight. You get a night off because this was kind of a lot for us. You did a good job. So here we go. Elastic collision. That's when gas particles collide, and what do? Transfer energy. So overall, the system energy stays the same. Right, so energy is not created, not destroyed, it's just transferred. Good. That's out in the hall. Is that Zach? No, you can stay. You're fine.
You want me to shut the door?
No, you're fine.
Shut the lock
No,
door.
you're okay. I know you really want to go out there. You're fine. 25. Explain the relationship between absolute temperature. What's that?
Who was that?
Who are you talking to out there?
What?
Who are you talking to?
Justin something?
Okay.
Probably.
What's absolute temp? I say absolute temperature. You guys should all think this scale.
The measure of kinetic
That's the definition of temperature. Good job. Measure of the average kinetic energy. If I say absolute temperature, you should think this temperature scale. Kelvin.
Kelvin. I said
Absolute is Kelvin. Okay. So kinetic energy and Kelvin. If we put it on an axis here, X and Y, kinetic energy. This is Kelvin, right? Temperature in Kelvin. Charlie, what's the graph look like?
Well, it's proportional to C.
Yeah, directly proportional. Good job. Directly proportional. Good job. So that's the answer to 25. 29. It's kind of.
Oh, we're
Yes.
on this side?
Yeah, we're on the other side. 29. What's significant about absolute zero? So 0 Kelvin. What's significant about that? Taylor. All motion stops. Very good. 30. By what factor does the average kinetic energy in an aerosol container increase when the temperature is raised from 300 to 900? I'm ignoring Celsius because that's not part of the deal here. So Bree, what do you think? Factor of 3. Where'd you get that from? Yes, if you divide 900 by 300, you get 3. So if your temperature increases by a factor of 3, kinetic energy increases by a factor of 3. Good job. 33. Evaporation of a contained liquid with that of an uncontained. All right, so here's an uncontained liquid. If I put the top on it, it's contained. What's the difference, Kayla? So if I take the top off, we'll start there. What happens if this starts evaporating? What happens? It's kind of a trick question. Someone help. I put her on the spot there. Evan?
Particles leave the container, and then when it's closed, they stay and go back in.
Right. So if it's open, nothing happens. It just evaporates and goes into the room. But if it's sealed,
Dynamic equilibrium.
right, you have evaporation, and you said it goes back. That's condensation. So both occurring at the same rate is dynamic equilibrium. That's what happens if it's closed, a contained liquid. All right, let's see. Steph, next one. Explain vapor pressure and dynamic equilibrium. We kind of just did that.
Vapor pressure is the pressure caused by a vapor particle collision.
Good job.
And dynamic equilibrium is when a substance condenses and evaporates.
Good job. So in this closed container, eventually this dynamic equilibrium is happening. What builds up here? What did I call that yesterday? Or it was yesterday I showed the video, or Monday? What about Monday? But what builds up in here? Vapor pressure, but what did I call it? Anyone remember? Well, what's this? Both happening at the same rate. What's that called? Equilibrium. So what builds up in here?
Sure.
vapor pressure, but a specific type of vapor pressure that only happens when it's sealed. It's called equilibrium vapor pressure. That's what it's called. Equilibrium vapor pressure. That's what it's called.
I don't know.
So when you have equilibrium occurring, you have vapor pressure building up. It's called equilibrium vapor pressure. In other words, that vapor pressure doesn't change. It doesn't get greater or smaller because there's a constant rate. Next one, explain why increasing temp of a liquid increases the rate of evaporation. Xavier, what do you think? I think that's 35.
Heat breaks the forces of attraction.
Good. So you gotta add one more sentence to that. So if you increase the temperature, you're adding heat. That heat allows the liquid to break the forces, and then what? Evaporates faster or slower? Faster, right. So the liquid, if I were to heat this up, it would evaporate very quickly because we're giving it more energy to break the forces and evaporate, turn into a gas, right? Evaporate. So you're giving it more energy, which breaks the forces faster. 36. The answer is no. Why? How come equilibrium, Devin, can't be established in an open container?
Because you can't condense.
There's no condensation. Good job. 37. If you increase temperature, what does that do to the vapor pressure? Jenny.
The vapor pressure increases.
Yeah, because there's more what? If you heat up a liquid, it evaporates more, so you're creating more. Well, let's say I close this and then I heat it up. The pressure could build and blow the top off, right? Why? What am I increasing in here besides the pressure?
The collision between parts.
Good, yeah. I'm kind of like a broken record. You guys aren't making me say the same thing over and over. The vapor particles build up and they start colliding more. So if you heat it up, you get more vapor, more collisions. That's why the vapor pressure goes up. All right, 38. Boiling and normal boiling. Let's see. Who have I not talked to? Go ahead.
Okay. The boiling point is the 100 degrees, right? 100 degrees. I just need to. So the normal boiling point is what the STP. The normal.
Standard temperature is 0 degrees. Water is not boiled at 0.
I just took one because no one said it.
Yeah, no, we're gonna roll with this. So just take out the T.
boiling point at standard temperature. That's what I said for the normal boiling.
Stop saying the temperature.
The boiling point at standard pressure.
There you go.
Oh, sorry. And boiling point is the temp at which liquid's pressure equals the vapor pressure.
Right, and that could be at any air pressure. So normal boiling point only occurs at standard pressure. Boiling point can occur at any pressure. That's the difference between the two. Both cases, your vapor pressure equals the air pressure. That has to happen. That's what boiling is. But normal means the pressure pushing down is 101.5.